Okay, let's move on to the next one. Now the question is L2 distance or is mean squared error the correct loss function? What could be a better loss function? So uh, for machine learning in general, including deep learning, we have four components: data, your model, your loss function, and then your evaluation. So we need to focus on the loss function because we know that convolutions are going to do a good job, but maybe there are some improvements that we can make on the loss function. So let's see how we can do that. So there were some comments on the chat. So I was reading that, which is okay, sounds good. So what is this perceptual loss? Why is it performing so good? If you look at it, this is the previous paper, this is this paper, and you're seeing more of the details of the shared of this tennis player. That's one application. The other one is you can also use the same framework to do style transfer. You start with a style, you have an input image, and then you want to translate this image to the style image that you started with. So why are we looking for a different loss function? For the mean squared error, if you take your image, you shift it 1 pixel to the right, or 1 pixel up, 1 pixel down, or 1 pixel to the left, you're gonna have a huge loss. But we know that these two images are the same. We just took it and push it 1 pixel to the right. So we need to look for a different way of enforcing the similarity between two images. And the idea of this paper is neat, is very neat. You can actually use a pre-trained neural network like VGG16 to give you the loss function that you want. And actually, you can use a neural network to give you a loss function. And here we are going to use VGG16 to give us the loss function. So we don't care about the neural network structure. There's an input image, you push it through a bunch of convolutions, and then you're going to output an output image, y hat. And let's say you want to do style transfer. You start with a style, and then here, if you're doing style transfer, yc is going to be x. What you want to have is x to be as close as possible to y hat, and then you push it through your VGG network. At some point, you're going to compare the outputs of those feature maps and try to see how similar they are to each other. Similarly, for this style, you can stop at some layer, pick up the feature maps, compare the feature maps, and that's going to give you a loss function. For instance, the loss function after ReLU 1, the first ReLU, the second ReLU, the third ReLU, etc. And then you're going to have a combination of these loss functions with some parameters, some hyperparameters that you're going to choose. And then you're going to combine your loss function according to that. So this is no more the mean squared error anymore. This is a loss function coming out of your network. This is Li is a loss function coming out of a VGG16, and this is pre-trained. And why are we using that? Because we know that a VGG16 is encoding some information about the content of our image. So it has some perceptive capabilities because we trained it on that task. We want it to be able to distinguish one image from another. So the same structure is going to help you solve both of the problems. For the style transfer, your YC is going to be X. So this is your input image. And your style, we are going to pick a style and then train one network per style. So you're going to keep that style. But then if you change your style, you're going to have to retrain a network. And for the super resolution task, you're not going to use the style part of your loss. So we are not going to use that. But YC is going to be the high resolution image. X is the low resolution one. The output is going to be y hat, and you want y hat to be as close as possible to the high resolution image. Rather than finding the mean squared error between these two, you push them through a VGG16, and then you compare the features at that layer. So you're going to have a feature reconstruction loss. And we know that our features are tensors. It has a bunch of channels, it has a height, and it has a width. And let's say this is the activations after the jth layer of our VGG. So this is after the jth layer. That is what J denotes. And how do you come up with your feature loss, feature reconstruction loss? You take the features, you compute the L2 norm, and then you average them. You find the mean. So basically, you're averaging over your channel, height, and width. And that's going to give you a loss. So basically, you're doing a mean squared error loss, but you're doing it on the features of a pre-trained network. This is smart. You can have a style reconstruction loss. That one is slightly different. For that, we are going to take a look at the gram matrix. And what is the gram matrix? It's going to tell you, it's going to give you information about which features are going to tend to activate together. So it's sort of a correlation between features. And how do you compute it? You take feature C and C prime, and then you're going to do a multiplication. This is a pointwise multiplication of this vector, phi j, because we know that each pixel is going to be a vector. So now you're picking two channels, C and C prime, and then you are doing the inner product of those two images. And then that's going to give you the correlation between one pixel, one channel, and the other one. And then you are going to use that to construct your loss. That's just going to be the Frobenius norm of the gram matrix coming out of y hat and the gram matrix coming out of, for instance, ys, your style. Okay. Now let's see how this method compares qualitatively when it comes to style transfer to the previous state of the art. That's your content. That's your style. That's the previous state of the art. That's what you get out of this method. Your style could be the Simpsons. Your content could be a cat or this person. And then that's going to be the output. And for each of these styles, you train the network. So if you change your style, you train another network. So far, so good. But what is this 11? What is that paper doing? So they had to do an optimization per each content image. So you pick a content image, you pick a style. The loss functions are the same as the loss functions in this paper. And then this TV stands for total variation. So it's acting as a regularizer. These are hyperparameters to balance the trade-off between different components of your loss. But the difference is that in this paper, you are taking X and pushing it through a neural network to give you Y hat, but 11 had to optimize over the image because there was no neural network before it. So per each content and style, they had to solve an optimization problem. And that's expensive. If you use 100 optimization steps or 300 optimization steps or 500 and different resolutions, the method in this paper is going to have that much speed up. So 11 is this much slower compared to what we covered here because of this neural network. And then you can also see the difference when you do super resolution. This is bicubic, this is SRCNN, the previous paper, and this is from loss of the features. So it's from this loss. And you can see more pattern compared to the blurry ones that you're getting from the previous one. So any questions so far?
In this case, are we training both the parameters of the image transform net as well as the loss network, or is the loss network just giving us a penalty that then applies to what our image transfer net spits out?
The loss network is fixed. There is no training on that.
There's no training ever. Okay, so that's just giving us basically a confirmation of how good or how bad our y hat is to then change the parameters of FW.
Exactly. So that one is fixed. What you're training is FW.
Got it. Okay, that makes total sense. Thank you.
So this is clever to use a neural network as your loss function. And this requires a deep understanding of these neural networks. So you take a pre-trained VGG and you use that in your loss function. Any other questions?
Are there any other uses or like cases where you could use another network for a loss function?
I know that there is a bunch of other papers that use it for evaluation metric. You can use it, for instance, to judge the quality of images generated by your generator. So you can also use it as a metric. For instance, I know that we had some discussions in the chat about peak signal to noise ratio. That's not the best metric. You can actually use a neural network there to give you a better metric that understands some of the concepts. For us as humans, it's very easy. We're going to look at these two images and we're going to say, yes, of course, this is better. But sometimes the signal to noise ratio is not the correct metric for that. It's going to give you a high signal to noise ratio, but then the image is crappy.
Yes, it seems like it can replace like when we usually do a qualitative judgment on something.
Yes. So that's a good way to put it. Any other questions?
This speed up table on the bottom right is really just talking about like the evaluation at the end of the day, right?
Yes.
Okay, because you'd have to train the image transform net on like a bunch of images and a bunch of ways of generating with like a certain style. And then once it's trained, it's fast for stylizing a picture.
Exactly. And the thing is, if you remember, the objective of deep learning is to give you an algorithm that you can use in production. So you don't care how much it took
Yeah.
to come up with that algorithm, but once you have it, you can use it in production. And this is exactly what you're gonna put as a post-processing step after your GPU is done processing an image. You're gonna put a neural network. It's gonna be very cheap, and then it's gonna give you high quality images.
Yeah.
And that's actually a way to boost the performance of your gaming engine or gaming environment.
It's cool.
It's gonna take a lot of effort to actually make that production ready because these gamers are not usually that happy customers. The slightest of glitches is gonna end up with bad reviews about your product. So it's a different thing. It's a research paper, but then making it production ready is a huge task. Okay. And a lot of engineering goes around it.